In the last class we proceeded up to the point where we divided the parameter space A B parameter space as A and B. This parameter space we had divided into boxes we said that this box which is between -1 and +1 this way and -1 and +1 this way. This box essentially represents a situation where in both the sides the map is stable, in the left hand side and the right hand side, in both sides the map is stable. So, you have got a evolution from period 1 orbit to a period 1 orbit. In this part we decided that in this part there will be a situation something similar to the border collision, something similar to the fold bifurcation or saddle node bifurcation, where but due to border collision, where a pair of fixed points are born and out of that one would be stable and another will be unstable. In this part we had decided that the situation will be similar, but what will be born are two unstable periodic orbits. So, here it is a situation similar to the saddle node bifurcation, but there is no node, both are saddles. And then we had gone to this part where we said that the situation is where a fixed point that was stable moves across the border and becomes unstable. So, A being between -1 and +1 means that the slope in the left hand side is less than 1 and that in the right hand side is less than -1. So, you have got a slope that is less than -1, a situation something like this. In this side the slope is less than 1, in this side it is greater than less than -1. As it moves you will have a situation like this. So, this was a fixed point that was earlier stable, now it has moved across the border and has become unstable, and so there can be a large number of possibilities, and we had explored the possibility of the existence of period 2 orbit. Up to this point we had come, and we had decided that this part will be divided into cases this was the range of occurrence. I should not say existence, because the period 2 orbit exists over the whole range, but this is the range of occurrence of period 2 orbit. Now, there are two boundaries we had decided. This boundary represents the situation A B is equal to -1, and this boundary represents situation A B is equal to +1, right. So, how did we arrive at that? We simply looked at the condition of existence of the period 2 orbit, and then we said that this orbit will be stable if the product of the two slopes A B is less than 1 in magnitude, and that violation happens in these two places. But we also saw that at this point there are two things that are happening. Not only that the A B becoming equal to +1 means that this fellow is now becoming unstable, not only that, we decided that in this part the period 2 orbit will exist for mu greater than 0, and in this part the period 2 orbit will exist for mu less than 0. Okay. So, if say we take a point here, that means we take some value of A B which is within this zone, means A is taken between these two parts and B is taken less than -1 suppose, then what is the behavior going to be? As mu is varied from negative value to positive value, we should understand that. See, when in the left hand side, when mu is less than 0, then the slope was between -1 and +1, a value of a represents that was between -1 and +1. So, for negative value of mu it would be stable, for positive value of mu it becomes unstable, and that is when the period 2 orbit exists. So, the behavior is simply a period doubling, bifurcation. So, if you now look at the computer screen, we can show that bifurcation for a specific set of parameter values. Okay. So, you see this is a bifurcation diagram drawn from top to bottom, where the period 1 orbit comes at this point, hits the border, and then a period 2 orbit emerges. Now, one important distinction between the standard period doubling bifurcation that you have seen so far is where you have a period doubling like this. There these two orbits emerge orthogonally from the original orbit like this, and in this case it goes like this. So, they go at acute angle, but remember in both the cases this unstable period 1 orbit continues, here also the unstable period 1 orbit continues. Okay. So, we have a typical period doubling induced by border collision here. What happens if you take a parameter, combination of parameter that is here? If you take a combination of parameter that is here, then a peculiar situation is there. So, that let me draw in a fresh page. We are talking about the bifurcation diagram. So, say this is my mu axis and this is my x. What will you see? Suppose this is mu is equal to 0. So, before mu is equal to 0 situation reaches, there will be a stable periodic orbit, okay, that becomes x equal to 0 at mu equal to 0 for this parameter, for this map. So, it goes and hits. After that, the fixed point becomes unstable and it emerges, and the period 2 orbit, yes, it exists, but it exists in the same side as mu negative. So, this is the period 2 orbit, which means the period 2 orbit exists in the same side where the period 1 orbit was stable, and in this side there is nothing stable. So, this is a typical subcritical period doubling. This is a typical subcritical period doubling. Subcritical means where the period 2 orbit exists in a same side where the period 1 orbit was there. It is, if you figure out how will it look in the typical smooth situation, it is like this, and at this point it becomes unstable, and the period 2 orbit, it actually happens. It actually happens in many smooth maps. So, this is the subcritical. So, here is a situation that is similar to that, but in a period doubling or in a non-smooth situation. Clear? So, we have understood what happens here. What happens here? The period 2 orbit actually becomes unstable. If you go across this, period 2 orbit becomes unstable, then what? Now, when the period 2 orbit still exists, but becomes unstable, and AB becoming equal to -1 means period 2 orbit undergoes a period doubling bifurcation. So, there is a period doubling bifurcation. So, this fellow becomes unstable, period 2 orbit no longer exists, then we have to face the next question: will a period 3 orbit exist? Will a period 4 orbit exist? Will a period, all these periodicities exist? Will chaotic orbit exist? We will have to face that question. Good. How do we face the question, will a period 3 orbit exist? See, the way we tackled the situation of the period 2 orbit was that we had say this is the 0 point, this is the x coordinate, and there was one point in the left hand side that mapped to the right hand side, and this point again mapped back. We had worked on this condition and then say that this orbit will exist so long as this point is in the left hand side and this point in the right hand side. Okay. In case of the, we are talking about this kind of a situation, you might notice that there can be a, okay, let me draw again to be clearer. So, a situation where you have got a map like this and here it is like this. You can see if you start from here, there can be a large number of iterates going like this, okay, and finally it's somewhere it will come back. Now you notice that here there is nothing that prevents a more than one iterate in the left hand side. So there can be two iterates in the left hand side, but once it falls here, it comes back, right. So it stands to reason that we should actually consider, if we consider period 3 orbits, that there are two possibilities. It could be 2 points to the left and 1 point to the right, or 1 point to the left and 2 points to the right. It will be more logical to consider the 2 points to the left condition. So what will we consider? We will say that here is a 0 point, there is 1 point here, another point here, and a third point here. So it goes like this, it goes like that, and it comes back like this. L L R orbit. So how we will work out the existence of this orbit? Suppose we start from this point. I would prefer to start from this point because that is actually determine the condition. So this point maps to the R, then comes here, then comes here. We will say starting point x n. So x n plus 1 is equal to a x n plus mu, because it is in the left hand side. Then x n plus 2 is equal to, now this fellow is in the right hand side, so it will be mapped by the right hand side equation b a x n plus mu, right. Now it has come here. Now again with the help of the left hand map, x n plus 3 is equal to a b a x n plus mu, right. Now this fellow must be equal to x n in order for this orbit to occur. So just solve this equation. If you solve this equation, you get a value of x n is equal to something, some expression you will get. Now that expression is the expression for this point. Remember, it is not this point or this point. Why? Because in order to find out for this point, you will have to map twice in the left and then on the right. While if you want to find this point, then you have to find first, you have to map first with the right map and then twice in the left map. That we have not done. So we have done for this point. Now notice that when this point is stable, this particular orbit is stable, this point must be to the left, because that is the condition that we have assumed. So the condition for existence of the period 3 orbit will be this number that you get here should be negative. This should be just consider the conditions of violation of this. This can be violated the moment it hits the border. Can this hit the border? This point? No, not before this fellow hits the border. So there is no point considering this point. Can this point go hit the border? If it does, then all the points will be in the left hand side. If all the points are in the left hand side, there cannot be a periodic orbit. Why? Because it is in each side is linear. If it is linear, it could be only a periodic or period 1 orbit, but you cannot have a high periodic orbit in a linear map. So the only condition is this fellow should be negative. that is the existence condition. So, this is existence condition. Can you find it? Not difficult, doable by hand. Now, what is the condition for stability? This particular orbit will be stable so long as there are 2 points to the left and there is 1 point in the right. So, the stability condition is a square b is equal to this magnitude, that should be less than 1, then it is stable. And obviously, this can also be violated in 2 possible ways. This can also be violated 2 possible ways. If we consider the period doubling condition, then a square b is equal to -1 is one violation condition. So, we obtain 2 possible conditions in which this orbit either ceases to exist or it ceases to be stable. Now, if we superimpose that on this, you will get a range that is something like this. Here is the condition for existence and here is the condition for stability that we just talked about. Similarly, you can find out the condition for existence stability for the period 4 orbit, it will be like this. And fine. So, there will be all sorts of orbits like this, and then let us check out if this is really true. Suppose I take a point here, which means I take this particular value of a and b, particular combination of a and b. If we do that, then as mu varies from negative value to the positive value, what will be the behavior of the bifurcation? What will we see? For mu less than 0, it is still stable because it is between a is between -1 and +1, and as mu goes beyond 0, then what happens? It is a period 3 orbit. So, it is a direct transition from period 1 to period 3. Let us see. I have taken a parameter in that range, right. It is a period 1 to period 3, direct transition from period 1 to period 3, where you see the bifurcation diagram looking like this. Very peculiar, cannot ever happen in a smooth map, but can happen in a piecewise smooth map. Similarly, if you take a point in the period 4 tongue, these are called tongues. If you take a point in the period 4 tongue, then you will have period 1 to directly to period 4 orbit. Want to see? Okay. Now, if now I take the parameter mu to be positive and I vary the bifurcation parameter a like this, what will you see? Here it will be a period 2 orbit, then here it will be chaotic orbit, here it will be a period 3 orbit, here it will be a period 4 orbit, and so on and so forth. And in between, what? If period 2 orbit is not there and period 3 orbit has not yet been born, so the periodic orbits will not be, any other periodic orbit will not be there, but still the orbit will be contained, bounded, and therefore the only thing that can happen is a chaotic orbit. Let me show an example. in between these two, between period 2 and period 3. Between period 2 term and period 3 term, I am taking a parameter value, and then we will see. Convinced? Right. So, this is a situation where there is a direct transition from a periodic orbit to a chaotic orbit. That is another peculiar thing that can happen in non-smooth maps. It cannot happen in smooth maps. Okay. As I told you, if you instead take A as the bifurcation parameter with the mu value kept at a positive thing, then what will happen? You will not have the period 1 to whatever, that kind of bifurcation. Why? Because it is already, mu is already positive. So, you will see, let us see, let us do that and you will be surprised. So, let us move it from 0 to 1, yes, fine. See. So, initially in this part it was period 2, then a narrow band of chaos, then you had period 3, then another band of chaos, then you had period 4, and again you have a chaotic orbit. What does it mean? It means that it is a period adding cascade. So, under such situations you are likely to see period adding cascades. In fact, in many experimental situations people have observed period adding cascades, and this forms one of the explanations of what mechanism can give rise to the period adding cascade. Clear? Okay. So, we have understood the whole character of the parameter space, and as I told you, the whole thing is symmetrical about this 45-degree line. So, whatever happens in this part, we have explored that. The same thing happens in this part if mu is varied from a positive value to a negative value. So, there is nothing new in this part, I do not really need to cover that. Now, this whatever I have said, that was the simplest possible case. Simplest possible in the sense that it is a one dimensional map, it is a piecewise linear map, and therefore, everything can be worked out by hand. Every situation of the combination of A and B, you can draw the graph of the map and work out by cobweb diagrams how the behavior is going to be. So, this is rather simple, but this forms the ground on which most studies on the behavior of non-smooth maps actually are done, because this can be easily worked out. Now, let us go to a relatively more complicated situation where we are considering two-dimensional maps. So, 1D is simple. So, let us go to the next level of complexity. Here what kind of situation are you considering? In a 1D map, we are considering a situation where there was two sides, each with a different functional form. Here also we will you will consider that. So, suppose this is my state space, but in this case we will have to consider x and y because it is 2D. In this two dimensional state space, there will be some kind of a border that divides the state space, and in this part there will be one functional form, say f1, and this is f2. Initially, let us consider the situation with hats. That means the state space is x hat y hat state space. Why? I will come to that later. This is necessary so that we can later deal with relatively small number of notations. So, it is actually a map where f of x hat y hat mu is given as f 1 x hat y hat mu, f 2 x hat y hat mu. This is for x hat y hat in say region 1, and this is for x hat y hat in region 2. So, that is the situation that we start from, where as I told you that in practical situations of piecewise smooth dynamical systems, switching systems, you are likely to come across this kind of maps, discrete and dynamical systems. So, what we will do? We are considering a situation where a fixed point, say it was here, for some value of the parameter mu, and then as you change the parameter, it hits the border. Now, in order to do that, obtain the normal form, it will be logical. The logical course of action should be that we will take only the local linear neighborhood of the border crossing fixed point. We will only consider the local linear neighborhood of the border crossing fixed point. Clear? Fine. This we will do through a series of coordinate transformations. Now, what is the first transformation that comes to your mind? First thing that we will do is, your x coordinate, y coordinate, the axis are anywhere. First thing I would like to do is to get the y axis here along the border. That will be the first thing that I would like to do, get the y axis here, so that the fixed point crosses the y axis. What kind of parameter or coordinate transformation will be necessary? We will do it by defining a new coordinate x tilde, which is x hat minus h of h is the equation of the h of y tilde. So, let the parameter be mu, parameter be rho, because I will come back to the mu parameter later. Let this parameter be rho. So, if you define it this way, then your x tilde, because I have already subtracted the position of the border, and therefore, my y axis always is my borderline. Borderline has been moved to the y axis. Okay. So, this and y tilde is equal to y hat, let that be the same, right. So, we had started with okay, let us start with G, so that we later come to F. So, this is G1 and G2. So, we have then the map as G of, it was x hat y hat, x hat is now written in terms of x tilde, it is x tilde plus h of y tilde rho comma y tilde rho. This is the map then. So, I have just substituted for x. Now, let us call it f. That is why I sort of kept f and started with g, because I wanted to later do with f. This is function of x tilde, y tilde and rho. So, that is the first coordinate transformation that we have done. Okay. So, the border is now the okay. Now, Now we need to do something, because now the border collision can occur for any value of rho, these are rho, for any value of rho. Now we would like to normalize that. So there will have to be a coordinate transformation, so that things are things happen for the parameter value of 0. So that is what we are trying to do now. So suppose at rho is equal to rho naught, the map has a fixed point on the border. So what happens? As you change rho, at some point it hits the border, and suppose that parameter value is rho naught, and we will now make some change, so that this thing happens at 0. So now we will say, now we need to do that coordinate transformation, but how the coordinate transformation is done, let me illustrate that with the next figure. So where did we start? We started with a border something like this, and at this point it was here at rho is equal to rho naught, and the position was like this. We define that the tangent along this direction, let that be called my say new y coordinate. Okay. Now if you have this and you have the map already, then you can find out where this vector maps. So suppose this vector maps to some place like this. Let that be called the x. So what have we done? We said that okay, at rho naught my position is here, then I will take a vector along the border, and we will say let that be my y vector. The y vector maps somewhere, and that vector we will call it the x vector. That will require a coordinate transformation. So we are actually making that coordinate transformation, so that if there is a unit vector E1 in this direction, and that maps to the unit vector E2, then this direction we will call y and this direction we will call x. So it is actually considering the unit vector. We consider unit vector and where it maps. Okay. So is the new coordinates understood? New x is this, new y is this. And how have we defined it? We said that we know that my fixed point is now on the border at rho is equal to rho naught. We make a tangent and take a unit vector E1 and find out where the unit vector maps in this next iterate, that is E2. We say that now my y direction is along E1 and x direction is along E2. That is the coordinate transformation that we have done. And this is my fixed point, new fixed point. New origin. If this is my new origin, this is x axis, this is y axis, then we can now write down the actual transformation that we have done. So we define new parameter mu bar is equal to rho minus rho naught. What does it mean? It means that border collision happens at mu is equal to 0, mu bar is equal to 0. Why mu bar? I will come to that later. I will later correct it. Okay. So that there are few things that we have done. We have changed the coordinate in terms of x and y, and we have also changed the coordinate in terms of the mu, the parameter. Now, what is the state space now? Our state space is now divided into two halves, one half this here, another half here, left and right. It is divided into two parts. For x bar less than 0, it is left half. For x bar greater than 0, it is right half. We can now define it. Earlier we couldn't. So, L is x bar less than 0, R is x bar greater than 0. No, they are different. I am now defining these bar quantities. We started with tilde, we started with hat, came to tilde, and then we are doing another thing, a new thing, which is the bar. That means, after that stage, after having reached the stage of the tilde, we only move the origin to the border, but then also having moved the origin to the border, then also we have to move it, so that we get the right coordinates. That is what we are doing, and for that we have defined the coordinates in a specific way, and the moment you define it that way, something will happen, you will see that. So, now we have the map as f x bar, y bar and mu bar. This can be written as, this is f1 of x bar, y bar, mu bar, and f2 of x bar, y bar, mu bar, in the two halves. This is in this half and this is in this half. Now, so far these functions, these were nonlinear functions. Initially when we started, these functions were nonlinear functions. We have only changed the coordinates, but in order to obtain a local linear representation, we have to locally linearize that. So, we take the next step of locally linearize these two. As a result, we will say this f x bar, y bar, mu is, it will be consisting of J11, the Jacobians, J12, J13, J21 and J22 times x bar, y bar plus mu bar times, here also the partial derivative with respect to mu have to be taken, which will be VL x and VL y plus the higher order terms for x bar less than 0, and similarly there will be similar terms for x bar greater than 0. So, let us first consider only the left half, and then we will do the same thing in the right half. There is nothing special about it. So, let us now write down what these guys are. For example, J11 is you have taken the partial derivative with respect to x bar, whose partial derivative f1, which is a function of x bar, y bar, mu bar evaluated at mu bar equal to 0. Now, this fellow we are considering the limit yes x approaches 0 minus and y approaches okay. Similarly, all these terms will have to be written. J12 is limit x bar approaches 0 minus, y bar approaches 0, partial derivative with respect to y bar whose f 1 x bar, y bar, mu bar. Okay. Similarly, j 2 1 is equal to limit x bar can you see? Yes. Okay. Additionally, we have to talk about these two fellows. These are the partial derivatives with respect to mu. So, V L x is again the limit, same limits, x bar going to 0 minus and y bar going to 0. This is now derivative with respect to mu bar of the first one. At similarly, V L y is limit x bar fine. So, we have defined all these fellows, and similarly in the if in the right hand side for x bar greater than 0, you will have similar quantities. So, let us first concentrate on the left hand side, we will come back there. Now, notice that the moment we have considered this particular thing, we have considered that unit vector in the y direction maps to the unit vector in the x direction. The moment we say that, what happens to these quantities? The moment we say that, notice unit vector along y direction means x equal to 0, y is something that has to map to x direction. Yes, no, j 1 2 is 1 and j 2 2 has to be 0. Okay. So, the moment we have imposed that condition, we have actually imposed the condition j 1 2 is equal to 1 and j 2 2 equal to 0. So, this fellow is 1 and this fellow is 0. Good. So, what is this now? You would notice that this fellow is nothing but the trace, because this two addition is the trace, this is 0, therefore, this must be the trace. So, j 1 1 must be the trace of the left hand side. So, what remains is this fellow j 2 1. If this is 1, your determinant is these two minus these two, and these two fellows product is 0, because this is 0, this is 1, and therefore, this is the negative of the determinant. So, j 2 1 is equal to minus so we have now arrived at this equation for the left hand side only, f x bar y bar mu bar is equal to plus the higher order terms, which we can ignore for now. This is if x bar less than 0. In the right hand side, you will arrive at the similar thing. So, this is equal to tau r 1 minus delta r 0 x bar y bar plus mu bar v r x v r y if x bar greater than 0. I am ignoring the higher order terms now, because we are obtaining the local linear representation. Now, let us consider these two fellows, these two. Notice that we are considering continuous maps. If the map is continuous, then that would immediately demand that this vector is equal to this vector, else the map cannot remain continuous. As mu changes, the map will become discontinuous unless these fellows are equal. So, V L x V L y must be equal to V R x V R y, which we can say V x and V y. Okay. So, we have arrived at that conclusion. Now, we make the final coordinate transformation, where we say x. Now, this is where we arrive at x. So far we are using tilde, hat, bar, but now we arrive at x. The final choice of the coordinate for our convenience is then x bar, but y has to be changed to y bar minus mu v y, and mu is mu bar times we assume that Vx plus Vy is not equal to 0, then only this works. If we make this coordinate transformation, then we have x, y and mu, right. In that case, your map will finally be written as x, y, mu, x, y as the coordinates and mu is the parameter, is equal to, in this side it is tau L 1 minus delta L 0 x y plus mu, then this is 1 0 for x less than 0, tau r 1 minus delta r 0 x y plus mu for so what I actually done, we have actually made a change of coordinate so far your y bar, where is the picture, choice of y bar was parameter dependent, but the moment you have done this coordinate transformation, y is no longer parameter dependent. We have freed the choice of coordinates from the parameters. Parameter is an independent thing that only makes the fixed point move. So, this is the 2D normal form. Just contrast with it the 1D normal form. 1D normal form was G1 x mu A x plus mu B x plus mu. This was for x less than 0 and this is for x greater than 0. This was the 1D normal form, this is 1D, and 2D normal form is this. How are they related? The derivation of the 1D normal form was far easier, but the 2D normal form is, as you could see, we have to go through a few steps. But the link is that if you consider in this 2D normal form the determinant is 0, then it becomes the 1D normal form. If the determinant is 0, it becomes a one dimensional normal form. So, any 2 dimensional system if you make the determinant 0, it actually becomes a one dimensional system. Here this line goes, and then the tau L becomes equivalent of A, and the tau R becomes equivalent to B. So, in your thought you should remember that the determinant is something that makes the distinction between 1D and 2D, but the equivalent of the slope in 1D is here, the trace. Trace represents the equivalent of the slope. So, if you make the determinant 0, the trace is nothing but the slope. But so long as the determinant is there, trace is not really the slope, it is actually a kind of derivative quantity, addition of the two cross terms. Okay. So, in the next class I will continue with this particular map, two dimensional map, and from there we will try to obtain it. Now, I will give you a clue to handling all these coordinate transformation. Now, see, we have done a series of coordinate transformations, and through that we have tried to sort of simplify the matter. Whatever may be the complication involved in the coordinate transformation, ultimately we wanted to arrive at something simple, and that is what we have done. Now, you could argue that okay, in the left hand side you could locally linearize it and get a map, get a matrix. In the right hand side also you could locally linearize and get a matrix, but these two matrices will have 4 terms here and the 4 terms there. So, naturally this representation with 2 matrices, each term containing non-zero and non-one terms, that will be more complicated than this one. You could argue that okay, I have a matrix in the left hand side, couldn't I simply by matrix manipulation obtain this? Yes, you can do that, right? You have a matrix, you know how to do matrix manipulation, and matrix manipulation nothing but coordinate transformation. It is basically the same thing as coordinate transformation. So, you could argue that no, I do not want to look at all these coordinate transformations, I simply want to do some matrix manipulation by which I want to arrive at this. Can you do that? You should be able to do that. I did all these procedures because that gives a geometrical intuition, because the fact that y axis maps to the x axis is important. Those things will not be clear if you simply do the matrix manipulation, but you should know how to do the matrix manipulation of a matrix that has the shape A, B, C, D to you should be able to do that. Okay, that is all for today. We will continue with the next class.